I'm Sauhaarda, and I'll be presenting Multimodal Multitask Learning for Autonomous Driving, a collaboration with Tushar Pankaj and Carl Zipser from UC Berkeley. Our lab uses 1/10 scale model cars to study autonomous driving in unstructured conditions like that present off-road. The small size of our vehicle allows for the collection of diverse data and the flexibility for low-risk experiments and iterations of our system. Autonomous driving is complex, with multiple behavioral modalities ranging from lane changing to turning and stopping. Our unique dataset models these real-world conditions by including annotated behavioral modes for driving. For the model car, these modes are direct, which drives on a path while avoiding obstacles, follow, which follows a leader car driving ahead, and furtive, which attempts to stay close to perceived boundaries. Our dataset is the first major sidewalk driving dataset, but is also quite large in size and comparable to existing datasets, especially in terms of the diversity of the data present. Multitask learning systems are those that predict auxiliary tasks in addition to the primary task necessary. Often, the inclusion of an auxiliary task related to the primary task increases the performance on the primary task. Our dataset is stored as a collection of packets we call data moments. Each data moment contains a pair of stereo camera images taken in 33 millisecond succession. These images are associated with 10 pairs of expert motor power and steering values taken every 33 milliseconds for 333 milliseconds. When our networks are trained, they aim to predict all 10 steps of motor and steering values into the future, building a planned trajectory from the input images. When actuated on the cars, however, only the final predicted value, 330 milliseconds in the future, is used. The remaining 9 predicted values are auxiliary tasks for our system, making it multitask learning. In multimodal architectures, a network takes in multiple styles or modes of user input. Our multi-net model takes as input the behavioral mode it should act in for the current scene. This secondary input is fused with the camera input data after initial processing and sent to a final late fusion network for final output. In practice, the initial processing is done via convolutional layer, and this is then concatenated with the modal information stored in a binary tensor and sent for further processing. The further processing is done via a convolutional layer and 2 fully connected layers, which outputs the 10 pairs of motor power and steering values. When the multi-net model is trained and its MSE validation loss is computed on the 10 outputted values, it exhibits considerably better performance in its loss measurement when compared with 3 separate MTL networks for each specific behavioral mode. The multi-net system is also more stable and exhibits much less overfitting than its MTL counterpart. When performance in individual modes is examined, such as this furtive graph shown, a similar pattern is replicated in which multi-net networks have lower loss than MTL networks, which continue to overfit. We also evaluated our model cars in live experiments. Follow mode was excluded from these experiments because the behavior of this mode is dependent on the behavior of the leader car. In the experiments, multi-net networks were superior to the MTL networks. However, the difference was less pronounced in the furtive mode as compared to the direct mode. The difference can be accounted for by the nature of the furtive mode, which involves driving much closer to perceived boundaries, which may incite more user correction through our autonomy metric. In reality, the multi-net furtive networks exhibited much more furtive behavior in comparison to the MTL networks. In this way, we can understand that our validation loss metric was a good indicator of performance, as it matches the autonomy metric for the direct mode and incorporates driving behavior into the metric for the furtive mode. The multi-net system presented is a deep learning methodology adapted for tasks involving multiple behaviors or modes. From the experiments conducted, it's clear that multi-net is more advantageous than multiple mode-specific networks. Future work can integrate additional sensory inputs such as GPS and accelerometer data into the multimodal input to the network. Finally, the approach can be extended to other applications involving multiple behavioral modalities. Thank you, and please check out our poster presentation. It's number 77. Thanks.
Hello everyone, my name is Verdi Adussi and